Hello and welcome to Earth Science, Lecture 27, Patterns in the Night Sky. This is an exciting time in the history of astronomy. A new generation of telescopes is scanning the depths of the universe. Increasingly sophisticated space probes are collecting new data about the planets and the objects in our solar system. Rapid advances in computing technology are allowing scientists to analyze the vast amounts of new data and then be able to model the processes that occur in planets, stars, galaxies, and even the universe as a whole. So in this lecture, we're going to discuss a few key ideas that will help us understand what we see in the night sky. Shortly after sunset, as daylight fades to darkness, the sky appears to slowly fill with stars. On clear, moonless nights far from city lights, more than 2,000 individual stars may be visible to your naked eye, along with the whitish band of light that we call the Milky Way. The picture on the right is actually an image I took from Sardis Lake, Oklahoma. So you can see right from top left to bottom right the band of the Milky Way. As you look at the stars, your mind may group them into patterns that look familiar in terms of shapes or objects. If you observe the sky night after night or year after year, you will recognize these same patterns of stars, and these patterns have not changed noticeably in the past few thousand years. People of nearly every culture gave names to the patterns that they saw in the sky. We usually refer to these patterns as constellations, but to astronomers, the term has a more precise meaning. A constellation, which, by the way, is a root word with, stella is star, so with the stars is what this means. So a constellation, in terms of astronomy, is a region of the sky with well-defined borders. The familiar patterns of stars merely helps us locate the constellation. So just as every spot of land in the continental United States is part of some state, every point in the sky belongs to some constellation. So this image here on the right just shows this idea. Here's the commonly known Orion constellation, but remember, in terms of astronomy, constellation just means the region of the sky. So the constellation Orion is actually this red boxed area that we see. It just so happens that the structure is inside of it. Because the planets and moons of the solar system all orbit the sun in roughly the same plane, the planets, sun, and moon all appear to move along a band around the sky known as the zodiac. Because Earth's moon cycles through its phases about 12 times every year, the Babylonians divided the zodiac into 12 constellations. The dozen constellations of the zodiac are Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. These names may be familiar to you as the astrological signs of the zodiac. Note again that astrology is not real, and also note for my students at least, you don't need to have these memorized by any means. On modern star charts, the entire sky is divided into 88 regions, or 88 constellations. Every star in the sky is within the boundaries of one of these constellations. Astronomers use constellations to roughly identify the area of the heavens they are observing. For a student, constellations provide a good way to become familiar with the night sky. For example, the constellation Orion is now defined to be an irregular patch of sky whose borders are shown. So here is what it would look like if you look up at the night sky on a really clear night, perhaps with some binoculars or a telescope. So here's the Orion. There's Orion's belt right in the middle. So here's the belt right here in the middle image. The Orion constellation is this bounded border like we talked about on the last slide. And then on the right is just an artist's representation of Orion. The stars of a constellation only appear to be close to one another. Usually what we see is only a projection effect. The stars of a constellation may be located at very different distances from us. As an example, the Orion figure shows the distances in light years from Earth to 4 stars in Orion. Although Bellatrix and Mintaka appear to be close to each other, Mintaka is actually more than 600 light years further away from us than Bellatrix. The two stars only appear to be close because they are in nearly the same direction as seen from Earth. Thus, most often, the stars that form a constellation have no actual relationship to one another whatsoever. The same illusion often appears when you see an airliner's lights at night. It is very difficult to tell how far away a single bright light is, which is why you can mistake an airliner, which is only a few kilometers away, for a star that is trillions of times more distant. Go outdoors soon after dark, find a spot away from bright lights, and note the pattern of stars in the sky. Do the same process a few hours later, and you will find that an entire pattern of stars, including the moon, has shifted in its position. New constellations will have risen above the eastern horizon, and some will have disappeared below the western horizon. If you look again before dawn, you will see that the stars that were just rising in the east when the night began are now low in the western sky. This daily motion, or diurnal motion, of the stars is apparent in time exposure photographs like the one you see on the right. So these are what you would call star trails. So this is a long exposure photograph. Someone left the lens of their camera open for a while, and as the stars moved through the sky, they left a streak behind. So what causes this? To understand diurnal motion, note that at any given moment, it is daytime on half of the Earth and nighttime on the other half. Earth rotates from west to east, making a complete rotation every 24 hours, which is why there is a daily cycle of day and night. But also, because of this rotation, stars appear to us to rise in the east and set in the west, as do the sun and moon. And so, here we can see this. So here's light from the sun coming in from the left, and the Earth rotating in a counterclockwise direction. So let's say you're an observer, looks like in Southern California, perhaps in Los Angeles, and you're viewing Cygnus. Cygnus, the constellation, is directly overhead. But 4 hours later, the Earth has rotated, and now Andromeda is directly overhead, not Cygnus anymore. So it appears like the stars streaked across the sky as a result. And this is what is known as diurnal motion. Always have to throw in a joke once in a while. I love the way the Earth rotates. It really makes my day. I'm sorry. So anyway, if you repeat your observations on the following night, you'll find that the motions of the sky are almost, but not quite the same. The same constellations rise in the east and set in the west, but a few minutes earlier than on the previous night. If you look again after a month, the constellations visible at a given time of night, say at midnight, would be noticeably different. And after 6 months, you will see almost a totally different set of constellations. Only after a year has passed will the night sky have the exact same appearance as when you began. This type of motion happens because Earth orbits the Sun. Over the course of a year, Earth makes one complete orbit, and the darkened, nighttime side of the Earth gradually turns toward different parts of the heavens. Hence, the particular stars that you see in the night sky are different at different times of the year. So this figure on the right shows which constellation is overhead at midnight local time, when the sun is on the opposite side of the Earth from your location. During different months for observers at mid-northern latitudes, including the United States, if you want to view the constellation Andromeda, the best time of the year to do it is in late September, when Andromeda is nearly overhead at midnight. But then, a couple months later, Earth has moved through its orbit around the sun, and now Perseus is directly overhead at midnight. And so on and so forth. So those are the two main motions of the Earth we'll discuss. The diurnal motion, in which the Earth spins on its axis, and so we see constellations move slightly throughout the night. Or we have this type of motion where the Earth orbits the sun. And it turns out that stars will typically rise 4 minutes earlier every single night, on average. The stars in a particular constellation appear to lie close to one another, but may actually be quite far apart, as we discussed previously. Because they may lie in very different distance from Earth, so this illusion occurs because we lack depth perception when we look into space, and so this is a consequence of the fact that the stars are so far away. The ancient Greeks mistook this illusion for reality, imagining that stars and constellations lie on a great celestial sphere that surrounds the Earth. Seen in the night sky, the stars all look equally far away. Therefore, it is easy to understand why the early Greeks regarded the stars as being fixed on this celestial sphere that surrounds the Earth. Although no such sphere actually exists, we still use this convenient concept to locate the stars and other celestial objects. For reference, we will identify 4 special points and circles on the celestial sphere. If you watch the sky over several hours, you will see that the stars remain fixed relative to one another while sweeping from east to west across the sky, as though they rotate around an axis that extends through the poles of the Earth. Although this apparent motion is actually due to Earth spinning on its axis, we designate a north celestial pole and a south celestial pole where an imaginary line through the Earth's axis of rotation intersects the celestial sphere. So we have a north celestial sphere, which is a point directly above the North Pole, and a south one as well. Now imagine a plane passing through Earth's equator that extends outward until it intersects the celestial sphere. The intersection of this plane with the celestial sphere is called the celestial equator. So in other words, it's just a projection of Earth's equator into space. It's a line, imagine a line actually painted on the Earth and extending it outward. And then we have the ecliptic, which is the path that the sun follows as it appears to circle around the celestial sphere every year. It crosses the equator at 23.5 degree angles because the tilt of the Earth is 23.5 degrees, something we'll learn about very soon. The north celestial pole happens to be very near the bright star whose various names reflect its location. You might have heard of it referred to as the pole star, Polaris, and the North Star. To an observer in the northern hemisphere, the stars appear to circle around Polaris, because it, like the North Pole, is the center of motion. If you live in the northern hemisphere, you can use the Big Dipper in the Ursa Major constellation to find the north direction by drawing a straight line through the 2 stars at the front of the Big Dipper's bowl. So that's what this is trying to show here on the right. So here's the 2 front ends of the Big Dipper's bowl. If you follow those and point a line, it will point you toward Polaris, which is north. The first moderately bright star you come to, again, is Polaris, also called the North Star because it is located almost directly over Earth's North Pole. The point in the sky directly above an observer, regardless of where they are on the Earth, is called that observer's zenith. The zenith and the celestial sphere for an observer at, say, 35 degrees north, which is fairly close to where we are, of the equator is shown to the right. The zenith appears at the top of the figure, so the Earth appears to be tipped. And if you took a time-lapse photograph toward the North Pole, you would see star trails like this, all circling around the center, which happens to be behind this tree in this particular image. For an observer anywhere in the northern hemisphere, the north celestial pole is always above the horizon. As Earth turns from west to east, it appears to the observer that the celestial sphere is turning from east to west. Stars sufficiently near the north celestial pole revolve around the pole, never rising or setting, and such stars are called circumpolar. So if we go back to that image for a moment, all of these stars that don't rise or set, so all of the ones that just barely stay above the horizon at all times, we call those circumpolar stars. Stars near the south celestial pole never rise above the horizon at all. All other stars have daily circles that are partly above the horizon and partly below it, which means that they appear to rise in the east and set in the west. And so this just shows you on the bottom what the star trails would look like if you're at different regions. So we saw for our location in the last image what it would look like at middle latitudes. At the North Pole, it would just look like the stars all go around you, since you're the center of rotation up there. And at the equator, it looked like they move straight up and down. The celestial sphere is a useful tool for describing the location of objects in the night sky. However, when you go outside, you can see only one half of the celestial sphere from any particular location, the other half being blocked by the ground from view. The location of any object in the sky can be described by its direction along the horizon and its altitude above the horizon. The direction is usually measured in degrees, clockwise from due north. In this figure, for example, the location of the object being described is located at 90 degrees along its horizon, or simply due east, and has an altitude of 50 degrees above the horizon. So this is just one way to quantify where something is. Our lack of depth perception on the celestial sphere means that we have no way to judge the true sizes or separations of objects in the sky. However, we can describe the angular sizes or separations of objects without knowing how far away they are. An angle measures the opening between two lines that meet at a point. A basic unit to express these is degrees. As we should hopefully know, a full circle is divided into 360 degrees and a right angle is 90 degrees. So as an example, the sun and moon both happen to span an angle of about 1/2 of a degree as viewed from Earth. Now, we aren't going to all go outside and stand out there with protractors in front of our faces, so there are some ways to make some estimates. The angular size or angular diameter of an object is the angle that it appears to span in your field of view. For example, as we mentioned previously, the angular size of the sun and moon are each about 1/2 a degree. Note that angular size does not tell us on its own of the object's true size. So the sun and the moon both have the same size in our sky, but we know they're very different in sizes. The moon is much, much smaller than the sun. It just happens that the sun is far enough away that it looks to be smaller. The angular distance between a pair of objects in the sky is the angle that appears to separate them. For example, the angular distance between the pointer stars at the end of the Big Dipper's bowl is about 5 degrees. You can use your outstretched hand to make rough estimates of angles in the sky. So the width of your index finger is about 1 degree, the width of your palm is about 10, and then your 3 knuckles on an index finger from the outside in are 3, 4, and 6 degrees, of course, on average. So you can make some estimates at least. For very precise astronomical measurements, we actually divide a degree into 60 arc minutes and subdivide an arc minute into 60 arc seconds. So we abbreviate arc minutes with the single parenthesis symbol and arc seconds with the double quotes. For example, we would read 35 degrees, 27 arc minutes, and 15 arc seconds in such a way shown. So this is how we would write it. So 35 degrees, 27 arc minutes, 15 arc seconds. So that's how we can use those symbols to describe things. So note, arc minutes and arc seconds, they sound kind of scary, but all they are is smaller versions of a degree. So in other words, 1 degree is 60 arc minutes, and 1 arc minute is 60 arc seconds. Just kind of like there's 60 seconds in a minute and 60 minutes in an hour. It is important to note that angular size does not indicate an object's true size, because angular size also depends on distance, as we just discussed with the sun and the moon. An object's physical size does not change as you move it farther from your eye, but its angular size does get smaller, making it appear smaller against the background. The sun, which is 400 times larger in diameter than the moon, has the same angular diameter, so about 1/2 a degree in the sky, as the moon. But that's because it's 400 times further away. So part A of this image tries to show that. Imagine this being the moon, this being the sun. The moon's closer and smaller, so to us they span the same angle as a result. So let's go ahead and try to close out this lecture with a couple of questions. Number 1. The location of any object in the sky can be described by its what and what? So how do we describe the location? Okay, in this case it is C, the direction along the horizon, and the altitude above the horizon. So the direction is usually measured in degrees clockwise from due north. Number 2, the angle that appears to separate two objects in the sky is also known as what? Okay, so in this case it's angular distance. So it's angular because it has to do with the angular quantity, but it's distance, not diameter or size, because we're talking about the distance between two objects, not how big one object is. So you can use your outstretched hand to estimate the angular sizes and distances in the sky. Your hand with fingers fully spread span about 20 degrees, and as we mentioned, your index finger is about 1 degree, with the back of your clenched fist about 10 degrees, in other words, the width of your palm. Number 3. Orion is visible on winter evenings, but not summer evenings, because of what? And I'm not sure what happened to C in this case, but the answer is C. Oh, there it is. So, spoiler alert, the answer is C. It has to do with the location of Earth in its orbit. I guess I accidentally added animations here. So, continuing on, let's see if it works for 4. Oh boy, it looks like I'm giving away answers here. Okay, well, I guess somehow animations got into this. So, how many arcseconds are in 1 arc minute? Well, we know there's 60 arcseconds for every arc minute, and 60 arc minutes for every degree. So 1 degree has 60 arc minutes, and each of those has 60 arc seconds. So you take 60 times 60 to get 3,600. And it looks like this one's okay. Question 5, the last one. The apparent path of the sun against the backdrop of the celestial sphere is called what? All right, so the path that the sun takes is known as A, the ecliptic. Okay, thanks for watching and have a great day.